Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore how open-source large language models reshaped the AI landscape, why they emerged, how they evolved, and why they've become one of the most important forces driving modern AI forward.
It really has been a seismic shift, and I think the core of our exploration today is that movement, the one pushing for transparency and accessibility in what are, incredibly complex systems.
Right. We're not just talking abstractly. We're going to look at the goals of this open movement and, maybe more importantly, get into the weeds of the technical roadmaps developers are actually using to build an open LLM from scratch.
And we have some really phenomenal material to work with. It's not just theory. We have these detailed engineering reports that outline the creation of specific, huge open models, like the Elon series.
And then we get to see the other side of the coin. We can contrast that amazing engineering feat with studies showing how these models are being used in the real world in really critical applications, things like intelligent tutoring systems or IT.
Exactly. And the thing that links all of this together is this clear, persistent drive to make powerful AI flexible, to make it testable, and to make it applicable for everyone, not just the handful of labs that pioneered the technology.
We're watching the era of the true black box start to close.
And that's a direct result of this commitment to open science. It's really happening.
Okay, that sets the stage perfectly. So let's start at the beginning, the origin story. Why did this whole open source movement gain so much momentum so quickly? It almost feels like the entire community decided practically overnight that the old way just wasn't working.
I think that's a fair assessment. The momentum came from this fundamental realization that access and visibility were being severely restricted. When the first truly powerful LLMs came out a few years ago, the technical blueprints you need to actually understand them, to replicate them, they were just missing.
Completely missing.
Almost entirely. And that lack of transparency was really created by two big bottlenecks for, the public and for academia.
I think I can guess the first one. It's all about the hardware, the sheer computational resources.
Precisely. To even get in the game, you need access to some of the world's biggest computers, the research community, universities, smaller labs. They just didn't have the infrastructure or the multi-million-dollar budgets.
And we're talking about a serious amount of hardware.
Oh, absolutely. The sources show that for a model like Elon, you needed something like 96 high-end NVIDIA A800 GPUs. And not just for a day, running continuously for months on end.
That's financially impossible for most academic groups.
It is, and it limited their role. They could study the final output, but they couldn't really challenge or understand the process of how it was created.
So researchers were effectively shut out by the cost of entry. What was the second big factor driving all this secrecy?
That was the proprietary secrecy, the industrial secrecy imposed by the big players themselves. For them, the detailed training processes were seen as trade secrets.
So everything from how they selected the data to the specific optimization steps.
Everything. It was all immediately classified as proprietary technology. It was their intellectual property, so the how-to guide was intentionally kept under wraps, away from the public and their competitors.
And that must have created a huge amount of frustration for the people who actually need to use this stuff, the engineers, the developers, the academics.
The demand for access became deafening. People weren't just asking for a high-level scientific paper. They wanted the actual operating manuals.
Which is exactly what the open models tried to provide.
Yes, that's where models like the Elon series, at 12 billion parameters, came in. They were explicitly created to break down that proprietary wall and democratize the knowledge. Their release was meant to be a comprehensive technical roadmap detailing every single step.
So anyone could, in theory, try to build one of these things from scratch.
You could argue it's been the most successful challenge to that kind of industrial dominance that the AI world has ever seen.
And this is where the open source idea is so powerful, I think. It's not just about releasing a paper that describes what the model can do. It's about releasing the actual model weights and the code. Why are the weights the really critical piece that unlocks that black box?
Well, think of it this way. Releasing a paper is like showing someone a beautiful photo of a skyscraper you built.
Okay, I can see the final product.
Right. But releasing the model weights, That's like handing them the foundation. Every single architectural blueprint and all the raw materials, it's everything.
So with the weights, you can do more than just look at it.
You can do three crucial things you couldn't do before. You can inspect the model's exact behavior, you can modify it for your own specific tasks, and maybe most importantly, you can verify how it acquired its knowledge. You can trace its learning process.
And that ability to verify the reproducibility, that's the bedrock of scientific progress, isn't it?
It is. It means the entire global community can now either build directly on those foundations or critique and improve them instead of just, accepting a proprietary result based on faith.
Transparency breeds trust.
And it dramatically accelerates innovation for everyone.
Okay, so we've covered the why, the driving need for this movement. Now let's get into the how. When they put out this comprehensive roadmap, what does it actually take? What's the sheer engineering scale needed to create one of these open models from the ground up?
The effort is just staggering.
Yeah.
12 billion parameters might not sound like the biggest model out there today, but the scale of the training data needed to give it real utility is enormous.
We're talking about the Yuan-based model here.
Right. It was pre-trained on approximately 1.7 trillion tokens. That's 1.72.
1.7 trillion. It's hard to even wrap your head around a number that big. It's not just a library, it's every library.
It is. And it's not just about the volume. It's a meticulously curated, highly diverse corpus of text from multiple languages.
Mm-hmm.
Diversity is absolutely non-negotiable if you want generalized performance.
Because the goal is for these models to be useful across different cultures, different languages, different technical fields.
Exactly. You can't get that by just dumping random data into the system. The training corpus is more like a carefully planned nutritional mix. Each ingredient is designed to build a different cognitive function inside the model.
A nutritional mix for an AI brain. I like that. So let's break down that data mix. What were the essential ingredients they needed?
First and foremost, they needed code. Vast amounts of programming code, mostly from places like Stack and GitHub. And this is critical, not just for teaching it how to program.
That's a really interesting point. Why is code so important for general reasoning?
Because code, at its core, is just structured, logical thinking. It's sequential, it's formal, it requires step-by-step problem solving.
So training on code helps foster what researchers call emergent chain of thought.
That's it. It gives the model a deep understanding of logical structure that goes way beyond just predicting the next word in a sentence.
Yeah.
It learns to think logically, not just talk logically.
Okay, so code provides a logical backbone. What about the facts? Where does it get its knowledge of the world?
That's where encyclopedias come in. They're the cornerstones for factual accuracy. They provide this structured, high-quality repository of human knowledge.
And it wasn't just, say, Wikipedia.
No, and this is a crucial detail. The Yuan team specifically integrated the Baidu Encyclopedia. This was a very deliberate choice to enrich the dataset with Chinese linguistic and cultural knowledge.
So they were actively working to ensure the model wasn't just a Western echo chamber.
Absolutely. It shows that openness isn't just about scale. It's about being thoughtful and culturally sensitive in how you source your data.
And what's the third piece of that data triumvirate?
There would be academic papers. Sourcing documents from repositories like ArXiv is essential. This material has complex structures, very formal language, dense scientific arguments. Training on it significantly enhances the model's reasoning capabilities.
It prepares it for tasks that require deep analytical skill.
Right, so you've got logic from code, facts from encyclopedias, and complex analysis from academic papers.
But the real genius here, as the sources show, is that they didn't just mix 1.7 trillion tokens together and hit run. They use a sophisticated 3-stage pre-training curriculum. It feels less like a fire hose and more like a carefully planned university degree.
It's absolutely a curriculum, and it's designed to overcome the known limitations of just continuous, uniform training. Because models, even with massive data, eventually hit performance plateaus.
They stop getting smarter.
Or they develop specific knowledge gaps.
Yeah.
So these 3 stages are designed to tackle those failure points one by one.
Okay, let's start with stage 1, the standard pre-training.
This is the foundation. The model just focuses on predicting the next token, sampling uniformly across that whole diverse data set. They do this until the rate of improvement starts to slow down significantly, until it hits that natural plateau.
And once it hits that plateau, they switch gears to stage 2, capability-enhanced pre-training. How do they break through that ceiling?
This is where it gets really strategic. The engineers noticed that while the model was very knowledgeable, its performance on comprehensive benchmarks, like MMLU,
The massive multitask language understanding benchmark.
right, Its performance was pretty weak. It was almost guessing on some of those tasks, which signaled that it didn't really have test-taking skills. It knew the facts, but it didn't know how to apply them in a structured, complex question-and-answer format.
So it was knowledgeable, but a bad test taker. How do you fix that in an AI?
You introduce educational assessments directly into the training mix. You train it on the structure of quizzes, on challenging analytical questions. This teaches the model not just the facts, but the format of evaluation.
And often these assessments include explanations for the right answer, right?
They do, and that's key. It helps guide the model to apply its knowledge algorithmically, not just rely on pure memorization. It's like having a study guide that explains why an answer is correct.
That's brilliant. What was the other big change they made in this stage?
They made a huge infrastructural change. They increased the maximum context length to 4,096 tokens.
Okay, 4,096 tokens. For anyone listening, if the context length is basically the model's short-term memory, how big of a deal is that increase?
It's a game changer. It's the difference between asking you to summarize a single paragraph and asking you to process an entire chapter of a book and then provide a coherent answer that references details from the very beginning.
It dramatically improves its ability to handle long documents and maintain a consistent line of reasoning.
A huge improvement.
So now the model is smarter and it's a better test taker. But there's a stage 3, long-tail knowledge-aware pre-training. What gaps could possibly be left after all that?
The long tail refers to all the niche specialized topics, the things that don't come up very often. Even after 1.5 trillion tokens, they found the model had persistent deficiencies in these uncommon domains.
So it would generate confidently incorrect information.
Exactly. Hallucinating on niche topics. So the strategy here was highly targeted. First, you identify those specific knowledge gaps through continuous testing. Then, you augment the dataset with new, focused content aimed only at fixing those deficiencies.
So it's not about adding more random data. It's like precision surgery on its knowledge base.
It's a very efficient, targeted approach, and it significantly mitigates those inaccuracies, giving a final boost to the model's overall depth and accuracy. It's a closed-loop system. Train broadly, assess formally, find the gaps, and then fill them.
So now we have this incredibly knowledgeable, highly refined base model. The next big challenge is turning that raw knowledge into something a human can actually use. We're moving from pre-training into fine-tuning and human alignment.
Right. This is the transition from a pure prediction machine, something that just guesses the next word, to a truly collaborative assistant. This process is called instruction tuning.
It's teaching the model how to follow directions.
Exactly. It shifts the goal from predicting tokens to tackling real human tasks, like summarizing a report or writing a creative story.
And just like the pre-training, this fine-tuning process also follows a kind of easy-to-hard curriculum.
It does. They start with the basics. They use foundational instruction data from widely used public datasets, things like FLAN v2, OpenOrca. This just establishes the baseline for how to handle simple, straightforward commands.
But the really interesting part is when they need to generate more complex instructions, things that are more nuanced than what you'd find in those public datasets.
Absolutely. The next phase is all about generating complex instructions, especially focusing on multi-turn dialogues. This is what's essential for improving the model's contextual reasoning, so it can hold a coherent conversation over many exchanges.
And what's so fascinating, maybe a bit ironic, is how they generate this high-quality data for their open model.
It's a great example of that competitive cooperation we see in the industry. They'll sometimes use a large proprietary model, like ChatGPT, as a data generator.
So they use their competitor's tool to build their own.
In a way, yes. They'll prompt the proprietary model to create a complex, multi-turn conversation on a specific topic. They'll ensure each turn asks a question that deepens the context and stays consistent with the conversation so far.
They're leveraging the capability of a closed model to fuel the open source movement.
It's incredibly efficient. They get these complex, high-quality instructions, and then they can feed those back into a generator to produce the ideal responses. All of that gets compiled into a massive, refined data set that's ready for their open model's instruction tuning.
So we've taught it knowledge, and we've taught it how to follow complex directions. The final step is teaching it. What? Taste. Manners. This is the human alignment stage.
You could call it that. This is the critical, ethical, and practical stage. The goal is to make sure the output isn't just correct, but also helpful, harmless, and generally aligns with what humans prefer to interact with.
This involves using datasets that have been manually annotated by humans, right?
Yes. Datasets filtered for quality and user agreement, like HHR-LHF. They gather pairs of responses, one that human annotators marked as preferred and one marked as rejected.
So the model sees a good example and a bad example side by side.
Exactly. And the training method, often direct preference optimization or DPO, directly teaches the model to maximize the probability of generating the good response and minimize the probability of generating the bad one. It's a very clean training signal.
It's essentially saying, do more of this, do less of that.
That's the core of it. And as the model gets better, they raise the bar for what counts as a good response, forcing it to generate progressively more nuanced and helpful text that meets really sophisticated human standards.
And the proof is in the pudding. What can a model built with this open roadmap actually do?
The results are pretty astounding. They directly challenge the idea that only the giant proprietary labs can get state-of-the-art performance. These models are capable of solving complex questions from the 2024 Gaokao China's National College Entrance Exam in subjects like history and biology.
Wow, that is not simple factual recall. That's high-level academic reasoning.
And beyond that, they can generate complex, multi-turn conversations about very specific topics, like space exploration, maintaining distinct personas throughout the dialogue. That's the level of capability that has really kicked off what we're calling the usability revolution.
Because now anyone can access and build on these high-performance models. Innovation is no longer confined to just a few mega labs.
That's the perfect way to put it. And we see this shift most acutely in specialized fields, like educational technology.
Right. Suddenly, instructors and small development teams have access to these incredibly powerful tools.
They do, and the labor savings alone are revolutionary. Think about automated content creation. You have systems like Quizmaster that use these accessible LLMs to automatically generate quiz questions directly from a textbook or lecture notes.
Something that used to take an instructor hours of manual work.
And now the LLM can handle it, which speeds up the whole assessment cycle. Students get feedback faster, and the instructor can focus on teaching. It creates a much tighter learning loop.
What about more specialized domains? Let's talk about math. General-purpose LLMs can often struggle with the precision needed for mathematical reasoning. What happens when you specialize an open model for that task?
The results really highlight the power of fine-tuning. We have studies showing that even relatively simple open models, say 13 billion parameters, can reach performance levels similar to children in solving arithmetic word problems.
And how do they achieve that kind of jump in precision?
Through very careful, specialized fine-tuning that use domain-adapted datasets. For instance, applying the MetaMath fine-tuning method on a dataset called SVMP, which is all about simple arithmetic word problems. This targeted training teaches the model to focus specifically on calculation and problem structure.
Which means you could deploy these smaller, fine-tuned models as conversational agents, a kind of study partner that could help a student who's stuck on a math problem.
And that need for precision and reliability brings us to maybe the most important factor in a high-stakes field like education. Trust. Why is it not enough, or maybe even risky, to just plug a classroom into a giant proprietary model like ChatGPT?
Hallucinations have to be the #1 concern.
It's the biggest one. LLMs are notorious for making things up, for generating factually incorrect answers because their goal is to sound plausible, not necessarily to be truthful. And second, a big proprietary model is trained on the whole internet. Its knowledge might not align with the specific curriculum an instructor is trying to teach.
So how does the open movement solve this grounding problem? How do you ensure the answers are reliable and traceable back to approved content?
The solution is a technique called retrieval augmented generation, or RAG, and we see it used really effectively in systems like the virtual teaching assistant, Jill Watson.
So Jill Watson has an LLM at its core, but it's on a leash, right? It can't just make things up.
Exactly. The RAG pipeline keeps it tightly constrained. When a student asks a question, the system's first step isn't to ask the LLM. The first step is to search a database that contains only instructor-approved materials: the course textbook, lecture slides, notes.
So it retrieves the most relevant authorized passage first.
And then comes the augmented generation part.
Yeah.
It feeds the student's question, and that retrieved passage to the LLM and instructs it to generate an answer based only on the information in that passage.
Which provides that crucial grounding. It makes the answer completely traceable back to the source material.
And that dramatically increases trust for both the student and the instructor. It's a really smart piece of engineering that uses the LLM's language skills while mitigating its biggest risk.
So let's talk about the big picture, the competitive dynamic. Is this open source movement really competing with the huge closed labs, or is it more of a niche academic thing?
Well, that gets us into the idea of competition, cooperation, and what I'd call the small model advantage. The whole ecosystem is stronger because of this competition. Every major open release pressures the proprietary labs to be a bit more transparent.
And every proprietary advance pushes the open community to innovate faster.
It's this incredibly rapid, virtuous cycle.
I think a lot of people assume that in AI, bigger is always better, that the largest model will always win on the benchmarks. But the sources we have show some really surprising counter-evidence, especially in specialized areas.
They absolutely do. In a really compelling study on conversational intelligent tutoring systems for second language learning, in this case, Korean smaller, specialized, fine-tuned models actually performed as well as, or in some cases better than, both GPT 3.5 and the much larger GPT-4.
Wait, a smaller model beat GPT-4 on a complex task? Which models were these?
They were specialized small language models, or SLMs, things like Llama 2 Code DPO13B. When they were evaluated using metrics designed for conversational quality metrics like Sacrable-AU and Meteor, these specialized open models got better scores.
What do those metrics actually measure that made the smaller models look so good?
Well, they're essentially measures of fluency and accuracy. Sacrable-LEU looks at grammatical structure and precision. Meteor is a bit more sophisticated. It understands synonyms and stems, so it's a better judge of overall meaning and context.
So a 13 billion parameter model outperformed a model hundreds of times larger on meaning and context.
That is a profound finding. It means the development team can get incredibly high-fidelity results for a niche application without the massive cost and latency of using a giant general-purpose proprietary model.
It confirms that these open-source models aren't just a curiosity. They're becoming a foundational, cost-effective part of the global AI infrastructure.
But it's not always just about competition. We're also seeing a lot of hybrid approaches where open and closed models work together.
Right. Tell me about Sammy, the AI social actor.
Sammy is a great example. It's designed to help build social connections in online classrooms. It uses the linguistic fluency of a generative AI, in this case ChatGPT, to create really engaging natural language.
Yeah.
But that's only half the system.
What provides the structure and the grounding?
It combines that LLM with classical knowledge-based AI methods, specifically knowledge graphs. So if the LLM is the brilliant improvisational actor, the knowledge graph is the highly organized director behind the scenes.
And what does that classical AI part actually do?
It handles the complex logical functions. Things like social matchmaking based on shared student interests, or even providing an internal explanation of its own reasoning. The LLM handles the fluid, natural language, but the knowledge-based system makes sure the response is logically sound and grounded in the actual student data.
So you're using the LLM for its fluency, but a more classical AI structure for logic and reliability.
A hybrid model that really leverages the best of both worlds.
We've talked about the incredible utility and the technology, but with open access comes responsibility. Let's get into the ethical application and governance.
This is the fundamental tension, isn't it? Transparency fosters incredible innovation, but that same openness introduces risks of misuse. And all of our sources, while they focus on applications, they consistently highlight the need for responsible and ethical use, especially around things like algorithmic bias and data privacy.
So if LLMs are these classic black boxes, how are developers building systems that people can actually trust, especially in high-stakes areas like grading?
It starts with explainability, XAI. We see studies on systems like SQL tutors that show a direct link. When the system explains why it's giving you a certain hint or recommendation, students' trust in the system goes up significantly.
Understanding builds confidence. But even if I understand the why behind a hint, how do we govern the process itself? Especially when we know a single LLM can hallucinate.
You use multi-agent frameworks. You essentially create a team of specialized AIs that check each other's work. A system called EVA AI, used for automated grading, is a perfect example of this.
Tell me about the agents in EVA AI. What are their roles?
You have at least three. There's the grader agent, which does the initial assessment. Then you have a reviewer agent, which scrutinizes the grader's work. It's like an instant peer review for every single assignment.
Can you give an example of how that catches an error?
Absolutely. In one case, the grader agent had a classic hallucination. It claimed a student's code had a typo in a variable name. It was just factually wrong.
And that would have led to an unfair grade.
It would have. But the reviewer agent, acting as that critical safeguard, detected the factual error, overruled the grader, and corrected the final grade back to full marks. It's an AI quality control system.
And there's a third agent, the teacher.
Right. The teacher agent can enforce overarching policies, like telling the reviewer to be more lenient on minor technicalities, ensuring the grading is fair and consistent with the instructor's philosophy.
So AI is now its own internal auditor. But no matter how good these systems get, the human has to stay in the loop. Where does that human governance come in?
A great example is in fighting plagiarism. An LLM can write a very sophisticated essay. So, to ensure academic integrity, assessors are now using LLMs to help them prepare for oral exams or vivas that follow up on a written submission.
The goal isn't just to retest the content of the essay.
No, the goal is to assess the student's intellectual ownership of the work. The questions are designed to test things an LLM can't fake. Real familiarity with the text, the ability to discuss the concepts, the ability to critically expand on the ideas when challenged.
So the LLM helps generate the questions, but the human makes that critical judgment about the student's actual understanding.
Exactly. It leverages the LLM's speed and personalization, but keeps the human in charge of the crucial ethical evaluation.
And that feels like a perfect picture of the path forward. It's all about building infrastructure and specialization. Open source tools are becoming the foundational pieces of these new AI systems.
They absolutely are. Look at the rise of things like vector databases. Open source tools like ChromaDB are fundamental for these RAG pipelines. They allow a chatbot, for instance, to efficiently index and retrieve very specific contextual information to ground its answers.
It's the difference between a library with a super efficient digital catalog and just having to ask a librarian a question and hoping for the best.
That's a great analogy. And this infrastructure is all aimed at one thing, especially in education: creating more efficient, individualized, and truly adaptive learning paths for students.
And the ultimate goal there is solving the assistance dilemma, knowing when to help a student.
Right. Students often don't ask for help when they need it, or they ask for too much help and don't learn. So systems like Transformer 4 HELP are now using transformer architectures to analyze a student's actions, every click, every input, to proactively predict the exact moment they're about to get stuck.
The system can actually forecast a moment of cognitive struggle.
It can, and that allows it to offer a hint or some scaffolding at just the right moment, bringing the AI tutor's performance much closer to that of an experienced human tutor.
So the future really is about efficiency and specialization. We saw it with the specialized math model, the language learning models. The biggest, most general model isn't always the best solution.
The trend is clearly towards smaller, highly efficient open models that are optimized for specific tasks, and that confirms their viability as a central global infrastructure. It lowers the barrier to entry for everyone.
So this open source movement is shaping tools that don't just answer questions anymore. They're actively participating in these complex cognitive and ethical processes, offering a future for AI that's more customizable, more inspectable, and ultimately more democratic.
We started out by saying that open source LLMs emerged from this critical need for transparency to break down these huge computational and proprietary walls. And now, given what these models can do, from passing college entrance exams to managing ethical grading agents, the question for the future isn't just how we build them. It's who gets to decide the governance rules for these foundational pieces of open digital infrastructure. If anyone can build a high-performing, specialized model cheaper and faster than the big industry players, what does that do to the centralization of power in AI? That, I think, is the real challenge moving forward.
That's a powerful thought to leave our listeners with. Thank you for walking us through the origins, the incredibly detailed technical development, and the crucial impact this open movement is having.
It was a pleasure.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.